data for the formulation of actionable insights. So now let's get to how data science works. So data science generally has 5 stages or 5 steps. The first step is capturing or acquiring relevant data. The second step is maintaining that data through cleaning and warehousing. The third step is processing the data. The fourth step is communicating the data, which is basically data visualization. And our fifth step is data analysis through different analysis methods like predictive analysis, linear regression, logistic regression, so on and so forth. So data science has many applications, and we can obviously only name a few. So the ones we've named are anomaly detection, like fraud, disease, crime, classifying data to make it easier to access data, forecasting, like weather forecasting and stocks, facial recognition, voice recognition, text recognition, and our basic recommender systems that are on our favorite streaming platforms like Netflix, Amazon Prime, YouTube, etc. So I hope you guys have grasped like kind of what data science is about through this super brief introduction. And now we're going to get into the fun hands-on part of it. So that brings me to today's agenda. So we have a panel, and they're all going to explain different parts of data science. So first, we're going to start with Anirudh, who's going to show you how web scraping works. Then we have Nityam, who's going to introduce you to data pre-processing. Then we have Alia and Vaibhav, who are going to show you a demo of how data visualization works. And at the end of the workshop, we're going to have a short Q&A session where all of you can pose your questions as to like based on whatever we've discussed in this workshop. So Anirudh, you can start.
Okay, so I hope everyone can see my screen. So I'm going to be talking about web scraping today. So usually as a data scientist, we always don't get the data we need. We don't always get ready-made data to do our analysis on, to pre-process, to visualize, and to make predictions. Sometimes we need to make our own data set, and to do this, we need to do web scraping. So what we generally do in web scraping is we take data, we find data on the internet that we like on a website. So for example, this Worldometer site, it has data on the coronavirus. It has how many cases are there, the number of deaths, the new cases and active cases, the people who are serious or are seriously in critical condition, the total cases for 1 million population, and all these details country-wise. So let's say we need this data for doing a project or for doing our own analysis. So how would we proceed? How do you proceed for this? So so firstly, we have a pandas library. This pandas library can be used to manipulate data. You can use it to make data frames and analyze our data. This NumPy library is for mathematical manipulation, and this request library is for submitting web requests to access the websites. This beautiful soup library is actually key in web scraping. This library helps us pass the data, helps us pass HTML and XML data, so we can read the data. So the best part about this beautiful soup library is that even when there might be small problems with the HTML code written by programmers, it cleans that, it passes that, and it gives us meaningful data. And this Matplotlib and Cbon library will be used for data visualization. Matplotlib is used for making graphs, and even Cbon is used for making graphs, which my colleagues will explain later. So we can start by running some of these by running some of these lines, and I can explain to you how it's done. So we are importing the libraries, and we need to scrape COVID data from this table, from this website. So this is the URL. So we can copy and get this URL, and I'm storing the URL in a website variable, and we're making a request. Using the request library. We're making a request to access this website and to get the text in this website, and that text we're storing here, and then there's a beautiful soup function, and this beautiful soup function is from the beautiful soup library which we're using to parse the data. This is the HTML parser we're using. There's also an XML parser, but here it's an HTML site, so we'll be using HTML parsing. So we need this entire data so that we can make sense out of it and use it for our analysis, which my friends will do. And now, if you look closely, this looks like a table to us, and we need to access this table. And this whole website is written in HTML. So if you pull the page source, you can find that this is a table. And this is some of the data is stored in a table. Most of you have done HTML, so you know how to write HTML code for a table. We have a table tag. In that you have t header, t body, t footer, and to store data in a row, like to store to add into a table row, we use the tr tag, and in that we have the td tag, the table data tag. So that's how we are storing all of this, lots and lots of data for all the countries where coronavirus is present, and we have stored it. So we need all of this data, and so all of this data is present in the t-body tag. So there's a find function. Beautiful soup provides us a find function. So using the previous soup variable, which we used to pass the HTML code in the site, we have used the find function to find the t-body tag. And the contents of the t-body tag are taken into a myTable variable. So here we have it. And now the next most important part is we need to store the data sequentially so that we can understand the data better. So as you can see here, this is a row, USA 31,420,331, and so on. These total deaths and these totally recovered active cases, and so on, so on, so on. There's a whole row. The USA thing is a whole row. And if we index this row, we can see that this ID, the hash you can see here is index 0, and this is index 1, index 2, index 3, and so on. So we need all this data. We need all this data. So how do we get this data? So first of all, I've created an empty list here, table data, in which we will be appending the values, the individual data for each country, like the total cases and the people who have recovered and the people who have died due to the virus, and the country name of the country. So what we're doing here is we introduce a for loop in which we are finding the table row, because each table row has countries like USA, India, Brazil, and all that. So now we've created another empty list, row data, which is an empty list, because we're going to be storing into this row data, and for each cell as in each cell, like this cell, which is total deaths for Brazil, or total cases for USA, is a cell. All of these are cells in a table. So we're going to be storing each cell into this. So now here, this is row data of 1, because this is 0. We don't need this hash and this 1, 2, 3, 4. We need only the country. So 0 USA, and then this, and then total cases, and then total deaths, and then totally recovered, and then active cases. So we start with 1, 2, 3, 4, 5, 6, and we go on till the end of the table row, till the number of columns we have. So we are storing country, row data of 1, and total cases, row data of 2. You can see this makes sense because this is 1, and then 2, the index starts with 0. So we're storing it as a dictionary, and we are appending this dictionary data item into this empty list, which we defined in the starting of into this empty list. So we are appending for each country. We're appending. So so this is an example of dictionary in a list for everyone who has done Python. They'll know what's a dictionary in a list. So now we have our data. Now we have our table data in the form of a list, dictionary in a list. Now we want to make it as a data frame. So we use the panda pd.dataframe function. So because Pandas is a very useful library in data manipulation, and in analyzing the data, because we can get to know a lot of things about the data. So this df data frame, we're storing it as a data frame, and this is to convert it into an Excel file, and we're storing it on our hard disk, on our computer's hard disk. So this df.to Excel function, you can store it as a CSV file as well, but for that you need to import a CSV file library. There's a CSV library, import CSV, and you can write into a CSV file. You can write all of this all of this COVID data, all of these into a CSV file, but I prefer Excel, so I've written it in as an Excel file. So this is going to write into the hard disk of my computer as an Excel file, and I just want to show how do you read data from your hard disk. So this is reading from the hard disk. We could have easily used this data frame to do our data analysis and to do our pre-processing visualization, but I prefer to just show you guys how reading is done. So this is the read Excel function. If we store it in form of a CSV, we could have used the read CSV function here. So we read the file, and the file has been read, and it's in the data frame data here. So now I just want to show you how the data is, So we run this head command, and what this head is, it shows the first. By default it shows the first five entries into the data frame, but since you have entered 10 here, it shows the first 10. So we execute this, and as you can see, USA 31,420,469 total cases. So if you go to your website, and you can see that you have this data, and we have done this within a matter of seconds. It doesn't even take a minute to actually get all this data. We've got all this data without without putting in a lot of resources, or without doing a lot of computing, or setting up live servers everywhere, and causing all those sorts of using up all those sorts of resources. We have simply done it with minimal resources, and we have done it very simply by just getting the HTML code. So the next step is pre-processing, which Nityam will be doing. So over to Nityam. Thank you, guys.
Good evening, everyone. I'm Nityam, and I'll be presenting the data pre-processing part for this CODS workshop on data science. I hope my screen is visible. Okay.
Yep.
Okay, so let's go on. So what is data pre-processing? So data pre-processing involves cleaning of data. And by cleaning of data, what I basically mean is that we usually receive data in its raw form, and raw data contains a lot of irrelevant and missing parts. So in data pre-processing, we try to reduce the irrelevancy and redundancy that is present in data. So without wasting much time, let's get started. So at first, we have Pandas Library to read the data set that had been created by Anirudh, and then we have a NumPy library to perform operations on data columns, as well as to create our own NumPy arrays and perform arithmetic or all kinds of operations onto those NumPy arrays. And at last, we have Cbon and Matplotlib, which are libraries which are used to visualize data. Right. So now we are trying to read the Excel file which was created by Anirudh, but I've converted it into a CSV file. And after that, I'm actually displaying the first 10 values of that data frame, just to get a hang of the data that we are dealing with. So this is how the data looks like. And next we have df.columns, which gives us an idea about the columns that we are dealing with. And next we have a df.describe, which just describes the data set in general. It tells us the rows, the mean of various columns that are present in those data values, the standard deviation, minimum, maximum, first quartile, second quartile, third quartile values of a lot of those columns present in the data set. So now just just to show you that this df.describe function works not just for the data set in general, but also for individual columns. So we have a total debts column in our data set, and applying the df of total debts.describe function to it, we get a description of individual data columns as well. So now when we usually get data, as I said earlier, we receive a lot of irrelevancy in the data. And by that, I mean missing values. And the missing values in data are usually represented by NaN values, where NaN stands for not a number. So here we usually involve the data preprocessing part usually involves with dealing with those NaN values and trying to replace them, or in worst cases, drop the whole column in itself. So here we have a total deaths column, and as we can see, there are 0 missing values and the percentage of missing values are 0. So we have no issues here. We've been lucky with this data column. Whereas if you see in the total recovered columns, we have two NaN values, and the percentage of missing values are 0.87%. Now, just for you people to keep in mind, usually when the number of missing values, rather the percentage of missing values, whenever they are less than 50% values which are missing in your data set, you can actually go ahead with dropping the column. My mistake, sorry. If you are rather more than 50% missing values, you go ahead with dropping the column. But if you have about, say, less than 20% missing values, you try to impute those NaN values with a suitable value. By impute, I basically mean replacing those values with a suitable value, which could be median or mean of the data column. So now giving you a whole overview of the number of NaN values that we have in our data columns. So as we can see, we have 8 NaN values in numbers, 216 in new cases, 219 in new deaths, and so on. So if you observe, our total rows were 229, and we have about 216, 219, 218, and 229 NaN values in a few columns. This accounts for over 95% missing values. So we really can't manipulate data to this extent, because this would hurt our data set. So we choose to drop these columns from our data set. So again, representing the same thing. And yeah, as I stated, we'd prefer dropping the total tests, new deaths, active cases, and new cases columns, because there are over 95% missing values. And as I said, if we have over 50% missing values in any of our data columns, we prefer dropping them. And here we have the df.drop function, which is used to drop specific columns from a data set. And once they are dropped, we see the revised data set, which does not contain new deaths, total tests, new deaths, active cases, new cases, numbers, etc. So now dealing with these data values, you'll usually come across strings. So as you can see, we've taken the critical cases column, and as I stated above, there are about 2 NaN values in them, which accounts for approximately 0.87% of missing values, and we can go ahead with the technique to replace them. So usually when you try to read data, you'll come up with string values in general, and we usually don't want string values. We want float or integer values to perform operations. So here is a little piece of code which is actually converting those string values into float values. But keep in mind, we have a lot of commas in these string values, and so you can't directly convert those string values into float or integer values. So here we have to convert these string values into float values by replacing those commas present in those values. So as you can see, we have a lot of commas in those strings, and now after performing that operation, we have removed the commas from each individual element in those in that column, and we've converted them into float values. Now we are going ahead with the box plot, and a box plot is basically used to show the number of outliers that you have in your data, and also to represent the skewness of your data. So as you can see, there are a number of outliers over here, and to get a better view of data, let's go ahead with the distribution plot, which shows that most of our data is skewed. By skewed, I mean that we have most of our data in one part of the graph. So if you see, if I try to draw a graph, I'll have most of my values towards the right, which indicates that it's a right skewed data. And the same is backed by the histogram as well. So whenever you have skewed data, the best replacement policy that you can come up with is the median replacement. we mainly deal with two major replacement techniques. We have the mean replacement technique and the median replacement technique. We use the mean replacement technique in those situations where the data is symmetric, and by symmetric I basically mean that you have less number of outliers. Whereas as we had seen in the box plot, there are a number of outliers and the data is skewed. That means it's not symmetric. So we have to go ahead with the median replacement technique, which is the best replacement technique for numerical data, which is skewed. So here we have the critical cases column, and I'm replacing all the values in it with the median of the critical cases column. And once we do that, we check the number of null values in the critical cases column, and those are 0, indicating that we have successfully removed all the null values and replaced them with the median. Now again, doing the same with the total deaths. Total deaths, again, we have, I guess, two missing values over there. And we're trying to replace, again, convert those string values into floats by removing the commas and then printing the final total deaths values. Here we have them converted into float. And now if we again try to plot a box plot for this, as we see, the middle line indicates the median, and as the median is shifted towards the right, we see that the data is right skewed. So when this basically indicates that most of our values are present towards the right. So, and as I've stated before, when we have most of our data skewed, the best replacement technique is to go with the median. Again, a histogram, again backing our claim that we have most values present at the right, and therefore the data is right skewed. And as I stated before, cause we have most of our values present towards the right, that is the data is right skewed, we go ahead with the median replacement technique. And we replace the NaN values with the median. And again, we have 0 missing values over there now. And now again, just to recheck with the overall data set and to check the number of missing values that we have now, we have about 2 missing values in total recovered and 77 total cases and 25 in total tests. Again, so total recovered cases, we'll again be performing the same operations. Again, be looking at the box plot. Again, number of missing values, and just to get a better hang of the distribution, going ahead with the histogram. Yep, and as we see, there are most values present towards the right, again indicating a right skewed data. And going ahead with the distribution plot. Yes, I mean, similar to the histogram, we have most values towards the right. And so therefore the data is right skewed again, and we go ahead with the median replacement technique. Same with total cases, we have about 77 values, still lesser than 50%. So we can go ahead with the replacement technique. Again, looking at the box plot, as I stated, the median is far towards the right. And so we have most values towards the right. So therefore, we go ahead with the median replacement technique. We have a number of outliers, therefore the mean replacement technique wouldn't be appropriate. Right, and then we drop all the column, we drop the null values, and as can be seen, there are no null values in total tests now. Now, if we go back and see total cases, there were total cases, we had 77 missing values, and we have another column having the name total cases again. So this means that there was an amount of redundancy in our data, and we choose to drop the total cases 1M column because it's the same as total cases column. So you'll also have similar columns in your data or redundancy in your data. So you will also have to at times drop columns which are similar and will just increase your work burden. So now after we have pre-processed everything, there are 0 missing values, and we have replaced the NaN values provided they were below the threshold of 20%. We have replaced them with the median, as that was the most suitable technique. And in case there were over 50% missing values, we went ahead and with dropping of those columns. I'd like to hand over the lead to Vaibhav and Alia now. They'll be explaining the data visualization.
Hey guys, I'm Vaibhav. So Alia and I will be taking over the data visualization for you. So before we get on to the hands-on coding of how to plot graphs, let me just give you a brief introduction of what data visualization is. As the name suggests, it's pretty easy. So data visualization is basically the process of creating an interactive visuals to understand trends, variation, and helps us to derive meaningful insights from the data. Now let's look into the libraries used in data visualization. Matplotlib is one of the popular libraries used in visualizing data. So it's a Python 2D plotting library which produces publication quality figures in a variety of hard copy formats and interactive environments across plot platforms. Uh, it, it can be used in Python scripts, Jupyter Notebook, and web applications. It's an open source and can be used freely. Now we can drop all sorts of visualization using Matplot, but let's discuss some of the important ones. So they are bar graph, pie chart, box plot, histogram, and scatter plot. So before we get started, I wanted to just basically make sure that my total cases are converted into an integer and remove the comma. So this is what I did, as Nityam has earlier explained. So, and then I realized that there were a lot of values for the country. So basically this country column consists of all the countries and the continents. As you can see, North America, South America, Asia, Europe, and Africa. So as we cannot derive a graph for so many contents, I basically sliced them and just wanted to make a plot a graph only for the continents. So this is what I did and saved it in df underscore continent. So now let's get into bar graph. So this over here is basically a bar graph, as you can see. So basically this PLT is basically pyplot, which you have imported earlier. So PLT dot bar df underscore continent of country. Basically this is the x-axis, and df underscore of continent total cases will be the y-axis. You can also give labels. By here you can see x label and y label as continents and total number of cases. And you can also change the scale and give a title to just make it look neater. So this is basically a bar graphs. So bar graphs are best used when we need to compare the quantity of categorical values within the same category. But we cannot use it for continuous values. So you need to keep in mind when to use a bar graph. Yeah, let's head on to pie chart. Pie chart is suitable to show the probability distribution of items within the same category. So yeah, so a pie chart is useless when there are a lot of items within a category, because there will be a lot of slices which will not make it look neat. So make sure of that. So pie plot is basically the code for pie plot is again plt.py of df continent of total cases, because we are plotting a pie chart for the total cases. And here labels is equal to df underscore continent of country. So that basically gives you the labels of each slice, say South America for the yellow and North America and so on. And this auto PCT, basically it rounds off. Here I've given one floating point. So basically it rounds off the percentage value to one floating point. So yeah, that's all about pie chart. And heading on to box plot, box plot gives statistical information about the distribution of numeric data divided into different groups. It is useful for detecting outliers within each group. So over here, again, the code for a box plot is this one, plt.boxplot df and continent of total cases. Again, as I said earlier, we can have a y scale and title, y label, x label just to make it look neat. So this basically is your box plot. So you have the middle line over here, which you can see that will be a median, the 50th percentile. And this the top end of the box is basically a 75th percentile, and the lower end will be a 25th percentile. And this over the lower one, the lower line, which you can see, that will be the lower whisker, which is represented by Q1 minus 1.5 IQR, where IQR is basically the interquartile range and Q1 is nothing but the 25th percentile. And the top line over here is basically the top whisker, and that will be represented by Q3 plus 1.5 IQR. Again, Q3 being the 75th percentile and IQR as the interquartile range. So basically this shows the skewness. We can also determine the skewness, as here it's a right skewed data. So that's all about box plot for you. Over to Alia, she'll be explaining about Cbon and the other graphs. Thank you.
Hi guys, am I audible?
Yeah, you're audible.
Okay. Hi guys, I'm Alia, and I'll be taking over the data visualization part from where Vaibhav left off. So I will be introducing y'all to Cbon. Now, what exactly is Cbon? So Cbon is basically a Python data visualization library that can be used to create a variety of plots used for statistical data analysis. It is based on Matplotlib. It's not a substitute for it. It's more like a complement for Matplotlib. And all the plots are still created using Matplotlib, but the Cbon API just makes it a lot more straightforward and easy to create attractive graphs and charts. To put it in simpler terms, if you're wondering why it might take like 5 to 6 lines of code just to plot, a decent looking box plot or a bar chart using Matplotlib, using Cbon, you can plot all kinds of graphs using literally one line of code. So if you're looking for a simpler way to plot attractive graphs, then you will love Cbon. All right. So we'll walk you through everything you need to know to get started. But before that, let's first understand what type of graph is used where. All right. So there are mainly 4 basic presentation types that you can use to present your data. And those are comparison, composition, distribution, and relationship. So we just saw what a bar chart was. We compared the different, how the total cases varied across the different continents. So evidently, bar charts are best for comparisons. Then you have these plots called line charts, which we will see very soon. And those are best when you're looking for trends or you want to predict future values. Then you have something called a scatter plot, which is great for relationships and distributions between variables. Then we have pie chart, which again, we just saw. And those are mainly used for simple composition. So we saw how it displayed the data in terms of percentages, right? So it's not really used for comparisons or distributions, but mainly for compositions. Lastly, we have a histogram, which is sort of a variation of a column chart, and it's mainly used to present distributions and relationships of a single variable over over a set of categories. Okay, so let's get straight to it. So like Vaibhav had explained before, if you look at our data set, the first 6 rows contain the continents, and only from the 8th row onwards, that's where all the countries' data starts from. So what I'm going to do is I'm going to create a data frame using this function pd.dataframe, where in this variable df_country, I'm going to store all the rows from the 8th row onwards, basically all the data pertaining to the different countries. And then I've taken another variable, df_continent, and here I'm going to store only the first 6 rows of our data set. So that's going to be all of the data corresponding to the continents. So let's execute that. So if I just display the df_continent data frame, you can see it just contains the data of the continents, and df_country will show you just sort of an overview of all the data of the countries. So let's get to our plots. Now, like I said, Cbon, all of your plots literally take like one line of code. So if you look at the syntax, it's the same for all of the plots. It starts off with SNS, which is our aliasing for the Cbon library, dot the name of your plot. Our first plot is the Kde plot. I will be explaining it very soon. And your parameter is, if it's a single variable plot, then your parameter is going to be just the column that you want to plot your graph for. So here we're going to plot the graph for the total tests column belonging to the df_country data frame. So I'm going to execute that. Yeah. So that's our Kde plot. Now, what is a kernel? Okay, Kde stands for kernel density estimate. So a kernel density estimate plot, it's basically used to visualize the probability density distribution of your data. All right, to put it in simpler terms, you can identify the spread or distribution of your data using this plot. So here you can sort of make out that most of your data falls within this range, right? So that's mainly what a kernel density estimate plot is used for. Moving on, we have the bar plot, which we just saw using Matplotlib, but you can see how much more simpler it is to plot it using Cbon. So executing that. So this is our bar plot. Just to run you through it again, bar plots are a very common type of visualization tool, and they're mostly used to show the relationship between numerical as well as categorical data. So here, obviously, country is our categorical data, and total cases is our numerical data. And this looks a little different from the one we just saw using Matplotlib. So I just wanted to show you that bar plots can be plotted both vertically as well as horizontally. So here I've plotted it horizontally. So that is a bar plot. Okay, moving on. We have the box plot. Okay, box plot, again, we saw this previously, but I'm going to run you through it again. Box plots are, they basically display your data according to its quartiles, right? So with box plots, you can easily identify the median, which is this line here. And you can identify if your data has any outliers, and you can also identify the range of your data. All right, so that's your box plot. Again, same syntax, SNS dot name of the plot, and your parameter is going to be the column that you want to plot your graph for. Okay, moving on, you have the violin plot, which is very similar to your box plot. Violin plots are basically a combination of the kernel density estimate plot, which we saw in the beginning, as well as the box plot. And it's used to visualize, again, the numerical distribution of data. So the difference here is, if you look at the box plot, it's of a fixed width, whereas for your violin plot, the width actually varies, showing you how much of the data lies within that range. So that is the violin plot. Moving on, you have the dist plot, which is similar to a histogram. It's actually a combination of the histogram and, again, the kernel density estimate plot. If you look at the curve, that's your kernel density estimate plot, and these bars here, that represents a histogram. So that's what a dist plot is, and it's very helpful when you want to visualize the distribution of your data, as well as if you want to identify the skewness of the data. So here we can easily tell that our data is right skewed, like Nithyam had previously mentioned. Okay, moving on, we have the LM plot. Now the LM plot, or the line plot, you can see the syntax is a little different, because here we're going to take two variables, right? So it's again very simple. We're going to say x, along the x-axis, we're taking the total tests column. Along the y-axis, we're taking the total cases column, and our data is going to be the df underscore country data frame. So very simple syntax. You just have to literally mention what your x and y axis is going to represent, and that's about it. So this is what our LM plot looks like. It's a very basic plot, which it basically shows a line along a two-dimensional plane, and it's used to see the correlation between the two attributes that are plotted along the x and y axis. So here we have total cases plotted against total tests, and you can see all of the individual points as well as a line passing through them. Okay, now if you look at the LM plot, you will notice that you can also identify the outliers here, right? So you can see that there are a few points that are sort of completely away from where majority of the points are. So you can see that just to accommodate this this one point over here, that's why the graph is so, scaled out and constricted. So let's do one thing. Let's try and remove that outlier and then plot this graph again, just so that it's in the scale is more understandable, and we can sort of see exactly where every point lies. So we're going to do that here. Now, this sort of comes under pre-processing, but the thing is, pre-processing and visualization sort of go hand in hand. You can't do one without the other. So here what I'm going to do is I've written a function called as remove outlier, which is going to take the column that you want to remove the outliers for as its argument. Okay, before we get into the function, let me explain how we're going to remove the outliers here. Basically, we're going to set a lower range and an upper range, all right? So our lower range is going to be, okay, let me explain it again. So you're going to have a lower range and upper range. We're going to fix those two values. And if any value is below the lower range, we're going to consider that value as an outlier and replace that value with the value of the lower range. And same thing with upper range. If any value is higher than the upper range, we're going to consider it an outlier and replace it with the upper range. So how we're determining the lower range and upper range, it's given here. So we've taken two variables, Q1 and Q3, which is calling this function quantile, which basically gives you 25% and 75% of the data. So our Q1 is going to contain the 25th percentile and Q3 is going to contain 75th percentile. And then we have IQR, which is going to find the interquartile range. That's Q3 minus Q1. So our lower range is going to be Q1, which we just found here, minus 1.5 times of IQR, and our upper range is Q3 plus 1.5 times of IQR. So anything that is either lower than this value or upper than this value is going to be considered an outlier and is going to be replaced by this value. So here, this is where we're calling the function remove outlier, and we passed the column total cases of the df_country data frame. So here what we're doing is we're calling this function, this numpy function called np.where. What this does is it works sort of similar to a ternary operator. So first it'll take the condition. If the condition is satisfied, the values get replaced by this. Otherwise, the values get replaced by this. All right. So what we've done is we've taken, this is our condition. If any value in the column total cases is greater than high contains the upper range, then we're going to replace it with the value of the upper range. If it's not higher than that, if it's within the range, then we're going to leave it as it is. All right. And same thing for the lower range as well. If there's any value that's lesser than the lower range, we're going to replace it with low. We're considering it an outlier, replacing it with low. Otherwise, we're going to leave it as it is. So let's just execute that. So now we're going to plot a scatter plot, which is very similar to the line plot that we saw, except here you'll see that because we removed the outliers, the graph looks a lot more understandable. All right, so let's execute that. And here you can see a scatter plot. So a scatter plot, it's very similar to the line plot. The only difference is that it just shows the scattering of the two attributes without the trend line. So it's also used for finding the relation between the two attributes. So here you can see each individual point and analyze each individual point. All right, so moving on here, again, I'm going to plot the line plot once again, just to show you how it looks after removing the outliers. So you can see it's much more understandable than the previous graph, that was this one. So this is what our line plot looks like. And you can look at the y-axis. Your scale is much more readable, and it just all makes a lot more sense now. So that was the line plot. Moving on, we have the joint plot, which is an interesting looking plot. So joint plots are useful when you want to visualize, again, the relationship between two variables, as well as their univariate relationship. So here you can see it's similar to the line plot that we just saw. But if you look here, you can see how each variable varies with time individually as well. And if you look here, you can see how the total cases column varies individually with time as well. Okay, moving on. Okay, lastly, we have our heat map. So heat maps are used to display the the correlation of different numerical attributes in your data set. All right. So here color scheme plays a very important role. You can visualize whether the correlation is, if it's a positive correlation or a negative one. So let me just execute it so you have a better idea. So here I've plotted the heat map only for 2 columns, that's total cases and total tests. And these values here show you how they're correlated. So you can see that total cases and total tests have a positive correlation of 0.52. So it helps a lot in, finding which columns are related to another, or finding relationships between 2 variables. Okay, so that's about it with the plots. Additionally, Cbon has the advantage of making your graphs look more presentable or understandable by applying different parameters. I'd like you all to check that out. I'll type it out here. So there's this one parameter called set_style. It's mainly used to set like the aesthetic style of the plots. You can mainly just to check it out. It's pretty cool. Then you have hue, which is used to decide which column of your data set can be used for color encoding. Again, this is also really useful and is used a lot. Then you have this parameter value known as palette, which is used to select the color palette that you want to use for your visualization. So Cbon has predefined color palettes that you could use, like there's pastel, there's bright, there's dark, and a lot more. Then you have height, which basically sets the height of your plot or your chart. So that's about it with all the plots. To conclude, let's see what inferences we can really draw from this COVID data set. One insight we got straight off the bat was which continent had the highest number of COVID cases, and that proved to be Europe. That was a very simple bar chart that told us that. And we also saw how the other continents stood compared to this. The pie chart that we saw also helped us see in terms of percentages how each continent stood compared to the others, right? Secondly, from our line plot and backed by our heat map, we can confidently say that the total cases is positively correlated to the total tests. So this means that when one quantity increases, the other does too, right? And looking at it from a sort of, a practical viewpoint, that absolutely makes sense, because we've heard about how countries claim they have more number of cases compared to others only because they conducted more number of tests for their people. So our analysis sort of validates that claim, and we have statistical proof for it now. Yeah, so now that we've plotted graphs, so here we plotted graphs mainly only for these 2 columns, that's total tests and total cases, just to show you the basics. So I'm going to leave it up to y'all to, plot the others and see if you can derive any more inferences from the data set. And I'm sure there'll be a lot of them. So yeah, that's it from my side. I'll be handing over to Maria now. Thanks for listening.
Thanks, Alia. Okay, so the floor is open. You guys can ask any questions you have regarding whatever's been discussed.